So Tuesday, we talked about extreme value theorem. Really, the big picture is we're just trying to find the highest and lowest points overall on the graph. And we know we're always going to rely on endpoints. We're also going to also rely on critical points. So we find f prime, we set the numerator and the denominator of f prime equal to 0. And then we just compare all those candidates along with the endpoints and see what's the highest and lowest point. Highest point is your absolute max. Lowest point is your absolute min. All right, so today we're talking about mean value theorem and Rolle's theorem, page 6. So mean value theorem and Rolle's theorem, now we're trying to guarantee a specific slope along the path of the graph. And this is what we can do to guarantee a slope somewhere along the curve. Okay, so I'm gonna have you guys copy this down here. Let me zoom in on this. Maybe it's not as clear on that. The idea is that I want us to see that we have a slope between the endpoints and then some slope that is going to match that slope between the endpoints. So I drew it really close, but I meant for it to be two slopes, one slope between the endpoints and one slope that is skimming the surface of the curve. Give me 1 second here. Okay, let me read this here. It says if a function is continuous over the interval and differentiable over the interval. So continuous means that we can't have any breaks in the graph. That's with a bracket. Differentiable means it's got to be a smooth curve all the way through, but we're going to use parentheses there. So I'm looking for these conditions written out anytime there's a mean value theorem or Rolle's theorem for full credit. Remember how with intermediate value theorem, I required that you guys showed me writing out functions continuous on the closed interval. And then with extreme value theorem, you're also writing out functions continuous on the closed interval. Now we're trying to guarantee slope, so we need both things here. We need the fact that the graph has to be connected, and it's got to be a smooth curve all the way through. We can't have any sudden sharp turns, otherwise we're not able to move forward and guarantee a slope that we're looking for. Okay, so we're going to practice writing out those conditions each time we're tackling one of these theorems. So as long as our graph is smooth and connected, then there exists a point on that open interval where the instantaneous rate of change equals the average rate of change. So the average rate of change is just the slope between the endpoints. So that's just algebra, right? We know how to find this. We know how to find slope. Find 2 points. They're always going to provide you the 2 endpoints. You just have to plug them back into the original function, get the y values, change in y over change in x. And after that, we're going to find the derivative, and we're going to set them equal to each other. Okay? What this allows us to do is we're able to pinpoint a place on the curve where this particular slope that we found between the endpoints exists. So let's say this slope between the endpoints ends up being a slope of 2. By us finding the fact that this is a slope of 2 and the graph is connected and smooth, there must be a place on the curve where the graph is going to experience an exact slope of 2 because we found an average rate of change. Okay. So when we do that, we're able to pinpoint the place on the curve that matches the steepness that we find between these 2 endpoints. All right, so let's look at number 1. And also, I want to highlight these specific words because we do need to, because on AP exam, they do reference these types of words here. So when it says instantaneous rate of change, this refers to the calculus portion of the problem. That's the exact steepness, okay? And the average rate of change is the algebra portion, is the slope between the endpoints. That's, I'm going to use color to indicate that distinction there. Okay, so when it says average rate of change, that's slope between the endpoints. Instantaneous rate of change, that's asking about this, that's derivative. That's finding the exact slope at a moment in time. Okay, so number 1, it says we have a function negative x squared plus 3x plus 10. This is a polynomial. On the interval, what is the average rate of change? So average rate of change is just the slope between the endpoints, right? So we're just going to plug 2 and 6 into the function. Let's get our y values, get our slope between the endpoints. Let's try that. Okay. And then this unit, you can use your calculator as well. So we just do slope between the endpoints, my average rate of change in y, divided by the change in x. Negative 20 over 4, which is negative 5. So imagine this scenario here. The graph is connected and smooth because we have a polynomial. So the graph may look something like this. What we found was that between 2 and 6, the slope of the graph is negative 5. Okay. So we can imagine that, right? We can imagine that to be true. So now what mean value theorem is going to do for us is, well, if this is a slope of -5, then there must be a place on the curve between the two endpoints where the graph is also going to experience a slope of -5, right? And we kind of imagine, right, that must be true. So we're basically, mean value theorem is going to be looking for this point, right? We're trying to find, okay, where along the graph is the curve going to also experience this slope that we found between the endpoints. I want to make sure that, for every thing that we talk about, if I can give you a visual so they can see it, so it doesn't just feel like a bunch of numbers we're just doing a bunch of number crunching. Okay, so now between 2 and 6, when does the instantaneous rate of change equal the average rate of change? So we're just basically finding a place on the curve where the slope is matching this particular slope. So now we can move on to our derivative process, f prime, because f prime is going to give us information about slope at every point on the curve. So what's f prime of x equal to? What's the derivative? -2x plus 3. Now, a derivative can be used in two different ways, right? We can either give it location and ask for the slope. I think that's the way that we're more used to doing, right? Because every time we do, point slope form, plug in the x value, let's find the slope. But it can also go the other way where we know what slope we're targeting and we just want to know where the graph exists. So it can go both ways. You give it location, ask for the slope. We can also give it slope and ask for the location. So that's what we're going to do here, because we know what slope that we want, but we don't know where the location is. So we're going to ask the derivative to tell us the location on the curve where there's a slope of -5. So then we just plug -5 in for our slope variable. Then we're going to solve for x. Subtract 3 from both sides. Divide both sides by -2. X equals what? 4. And the way that we call it, the solution that we're looking for, we say that C is equal to 4. C equals 4, that just means C just represents the x value solution that we're looking for. And you can kind of imagine that this to be true, right? At x equals 4, the graph is going to be experiencing the steepness that we're looking for, a slope of -5 that we found before with the average rate of change.
Is it always going to be like the middle of the two numbers? Or?
Yes, it'll always be between the two numbers. Yes.
Like exactly.
Oh, no. Yeah, but we know it's going to be. I mean, right now I'm just picking some random numbers, but it's going to have to be somewhere between. And we can guarantee that there must be a slope of -5 somewhere between. It's not going to be exactly between, but we can imagine that there has to be a slope of -5 somewhere along this path. Now, there may be more than one, but we're guaranteed at least one. Yeah, it could be at like 3.4. It could be at 3.5. It's not always going to be. It's just a coincidence that 4 landed directly between 2 and 6. Okay, so there is a distinction between mean value theorem and intermediate value theorem. Sometimes AP exams like to put problems back to back on the free response question and see if students can recognize, oh, wait, this is mean value theorem versus this is intermediate value theorem. So intermediate value theorem is the easier one. It's where on a given interval, you will have a y value at each of the endpoints of the interval. Every y value exists between these two y values. So IVT says if I have two endpoints that is that's provided, then I can guarantee that every y value between those two endpoints is going to be hit at least once. So if I want to guarantee some middle y value, I just have to show that my endpoints are above and below my target y value. With mean value theorem, it's more of, let's find the slope between the two endpoints. And then if I can, whatever slope I can find between the two endpoints, I know that there must be an exact slope of that value somewhere along the path of the graph. Okay, next page. Okay, so this is what a free response question can look like in terms of playing with these two different concepts. Okay, hot air balloon is launched into the air with a human pilot, the twice differentiable function. So whenever you see this twice differentiable, that just means it's a smooth curve. Twice differentiable means that I'm able to find the derivative twice, at least twice. So it's got to be at least at an x squared or x cubed level so that I can find the derivative twice. Otherwise, if it's a constant, then I can only find the derivative once, and by then it's going to give me a zero. So twice differentiable just means that I'm able to find the derivative twice, which means it must be a smooth curve. So we have data here that shows how high the hot air balloon is in relation to the ground at certain times. So that means at zero, when time is zero, the balloon is going to start off on the ground. 5 minutes later, it's going to be 40 feet above ground, then 70 feet, then drops down slightly to 65 feet, and then continues upwards to 80 feet. All this is within 30 minutes. Okay, so between 5 and 15 minutes, must there be a time where the balloon is exactly 50 feet in the air? What would you say? Okay, we don't see 50 here, but can we conclude that there must be a 50 somewhere along the way? Yes, why? How would you know from the data that the balloon is going to reach 50 feet up in the air? What numbers tell you that? Yeah, 40 and 70, right? It can't jump past 50 because everything is connected. So as the balloon is rising, it can't just skip over 50, right? It's got to pass 50 some point if it's going to go from 40 to 70. So this is basically intermediate value theorem. We don't need calculus to help us arrive at that conclusion, right? So we can say by IVT, by intermediate value theorem, since h of t is continuous, we don't need the fact that it's a smooth curve, but if it's a smooth curve, we know that it's got to be continuous. And our conclusion is, well, we're able to make this conclusion about 50 feet because we have a value under 50, we have a value above 50, so it's got to hit 50 somewhere in between. So this is where we write out, it's easy to understand, but it's kind of messy to write out. So since one endpoint is sitting at 40, and 40 is clearly less than my target, and my target is also lower than my other height, which is coming from h of 15. There must be a time t on the interval from 5 to 15 where h of t is equal to 50. Okay, so I think we just naturally are going to have an easier time with intermediate value theorem because the numbers are there. Even though we don't see those numbers, we can clearly see, okay, 40 to 70, I got to pass 50 somewhere between, especially if we know that the balloon is going to have to hit every height along the way. Okay, now the more difficult path is part B. It says between 20 and 30 minutes, must there be a time when the balloon's velocity is 1.5 feet per minute? So this one feels more abstract because, well, we don't have, we have the locations, but we don't have anything about velocity. So how can we figure out if we can guarantee this velocity? So this is where mean value theorem comes in. We're going to find the slope between these two endpoints, figure out how fast the balloon has what its average velocity is in this time period. Because if we can show that the balloon's average velocity is 1.5, then there must be a time when the balloon is going to reach 1.5 feet per minute. Okay. So our justification is this: our function is continuous. We're basically having to apply mean value theorem here because we're seeing if our slope can be guaranteed. So we have to write out our conditions here. We know our h of t is continuous because it's a smooth curve, so it's got to be continuous. And we know it's differentiable because they tell us it's differentiable. Continuous is with brackets, and differentiable is with parentheses. So let's find the slope between the endpoints, right? Let's find his average velocity. So change in height over the change in time. (80 minus 65 is 15. 15 over 10 is 1.5. So we know that over a 10-minute time period, this balloon is going to have it's going to rise 15 feet. And because of that, we know that his average velocity is 1.5 feet per minute. And if his average velocity is 1.5 feet per minute, there must be a time t when the balloon is going to reach exactly 1.5 feet per minute, right? It can't have an average velocity of 1.5 feet per minute without actually hitting that velocity at some moment in time. So we can say this by MVT. It's like this, right? If you're driving, if you're taking a road trip and you realize after how far you've traveled and how long it took you to travel that your average speed was 60 miles per hour, there's no way you could have made that trip and not reach 60 miles per hour at least once, right? So it doesn't mean that you're driving 60 miles per hour the entire way through, but if your average speed is 60 miles per hour, you got to hit it at some point. Same thing here, right? If its average velocity is 1.5 feet per minute, it doesn't mean that it's always traveling at this, but it's got to hit this velocity at some moment in time. Okay. Bottom of page 7 is the same process. One is IVT, the other is mean value theorem. Maybe we can come back to it. But I want to show you another variation of mean value theorem, and that is called Rolle's theorem. Page 8. So Rolle's theorem is virtually the same thing as mean value theorem. We're still going to go through the same formula. It's still f of b minus f of a over b minus a is equal to f prime of c. Okay. So I don't want us to think that, oh, this is a different theorem. It's the same theorem. It's just a more specific version of mean value theorem. Rolle's theorem is looking for a specific slope. Mean value theorem can be any slope. Your average slope can be between the endpoints can be 2, it can be 3, it can be 0, it could be 5. Rolle's theorem is asking to see, can I guarantee a slope 0? And to do that, I do need certain things to happen. I do need my y values to be exactly the same so that I can draw a horizontal line between the two endpoints. If I can draw a horizontal line between two endpoints, then there must be a place somewhere along the curve where I'm going to experience a slope 0, either a relative max or relative min or neither. But there's got to be a slope 0 somewhere between. Yeah, sorry, it's got to be a relative max or relative min. But we have the same conditions here. It's got to be continuous on the closed interval, so with brackets, differentiable with an open parentheses. And then we're still going to find the endpoints, but the endpoints have to share the same y value. Otherwise, they're not going to be directly across from each other. And if they're not directly across from each other, we're not going to get a horizontal line. Okay. So same process. We're still going to find the endpoints. We just want the endpoints to produce a slope of 0. That's all. Okay. And then we go through and we set it equal to the derivative, and we try to find the location where the graph is going to experience a slope 0. So here's example 2. Determine if Rolle's theorem can be applied on the interval from 1 to 2. If so, find the values such that f prime of c is equal to 0. So first things first, let's find our order pairs. Sorry, conditions. If we're looking at a polynomial, our polynomial will always pass all of our conditions. No sharp turns, no holes, no asymptotes. Let's spend the time to write out our conditions. Okay, so continuity is with brackets, and differentiability is with parentheses. Okay, next up, let's find order pairs so we can figure out the slope between the endpoints. So I have order pair 1, 0, and 2, 0. Is my slope going to be also 0? Okay, why is that? Is it because these are zeros? Is because they're the what? Does it have to be zeros, basically? As long as these numbers are what? The same, yeah. So it could be 1 and 1, could be 2 and 2, could be 3 and 3. But here we see 0 minus 0 over 2 minus 1 is equal to 0. Therefore, we know that because the two endpoints are experiencing a slope 0, I must be able to find a slope 0 as well. So now we can just find f prime, set f prime equal to the slope that we're trying to target, and find the location. Solve for x is equal to 3/2. Make sure that you're finding the slope between the endpoints. I see, this is what I've seen in the past where, let's say f of 1 is equal to 3 and f of 2 is equal to 3. And what I see some students do is, oh, they will replace f prime with 3 and then solve for x. What's wrong with that? Why do we not want to set f prime equal to 3 in this instance? It's not the slope, right? So make sure that you're not just, I know right now the numbers look like they match, but it's not because the 0 here doesn't mean that we use a 0 here. It's because the slope is also 0. So if I have 3 and 3, my slope is still going to be 0. We don't want to use a different number other than 0 if the numbers are the same. Okay, we don't know how to, we're not going to do any trig right now, but we can do number 4. Number 4, we're back to mean value theorem, which is the same thing as Rolle's theorem. It's just that if it says mean value theorem, the slope doesn't have to be 0. It can be another number, whatever we find between the two endpoints. But we're going to use the same formula. Okay, so we identify the two endpoints, find the slope. Once we find the slope, find the derivative, set them equal to each other, and then, or plug the slope into the derivative and figure out the location. Make sure that you're solving for x, and then that you're not plugging the slope into the x. You're plugging the slope into your derivative variable. But first things first, do we have any issues with our conditions? Are the conditions good to go? Yes, right. So polynomial, continuous, and differentiable. So we want to make sure we state those out. So let's do that. Okay, find the slope between the endpoints. So let's just find the y values, find the slope. Let's figure out what slope we want to. Guarantee. Right. Okay. So we know that there is a slope of -11 between the two endpoints. And now we're going to ask the derivative to tell us, okay, where is this slope going to exist on this curve? So we find y prime. What's our derivative? Where do we plug -11 into? The y prime, right? This is the slope. That's not location. We're looking for the location. We're trying to solve for x. So we're going to. Once we find our solution location, make sure that it lands between the two. Oops, sorry. -6 divided by +2. -3, sorry. We want to make sure that our C-value lands between the two endpoints. By the time we confirm that function is continuous and differentiable, we're guaranteed to find the location between the two endpoints. Okay. If a C-value lands at the endpoint, we would remove it. If let's say there was a C equals -2, this will not be good enough. Okay? So our C-value, mean value theorem is guaranteeing a C-value between, obviously not outside, and also not on the endpoints. So we only want to keep a solution that is between the two endpoints. Okay, I have some practice problems for us we can try. We can turn to page 10. Let's try 39 and 40. Here's our formula for mean value theorem. Slope between the endpoints first, then the derivative, and then set them equal to each other. Average rate of change is equaling the instantaneous rate of change. But make sure that we also write out our two conditions. If we're looking at polynomials, we know we're going to be able to pass through both conditions, but we need to spend the time to write them out. So we'll find f of -1, we'll find f of 1, find the slope between the two endpoints. So we should get a slope of 3. So now we're trying to figure out, ask the derivative to tell us where is there a slope of 3 on this curve. So find f prime, set f prime equal to 3, and solve for x. Whatever x value we find should land safely between -1 and 1. F prime is simply power rule, 3x squared plus 2. Put 3 into the slope variable. Solve for x. Take the square root. We get plus or minus √1/3. And both those numbers will be safely between -1 and 1. So we're going to keep both locations. So we have two different locations on this curve where the graph is going to experience a slope of 3. Both are valid. Okay, try number 40 and just want to walk around to see, do the steps make sense? Find your slope between the endpoints first. And then once you get the algebra out of the way, then you can take care of the calculus. Don't do the derivative. Yeah, so I do want to say that don't do the derivative first, even though it may feel like the easier thing to do. I think the danger with finding this derivative first is then you might end up plugging the numbers into the derivative, and that's going to throw you down. That's going to make you go down the wrong path. So I wrote out my mean value theorem this way so that hopefully you're forced to look at this first and see, okay, all right, let me just do the algebra first. That way I'm not accidentally plugging values into my derivative. I should not be. I see some students, they will find f prime first, and then they start plugging 2 and 0 into f prime, and that just throws everything off. So our endpoints produce a y value of 0. And so technically this could fall under Rolle's theorem because the slope between the endpoints ends up being 0, but mean value theorem is just it's a larger umbrella. It can handle any slope that you give it. But technically this could be a Rolle theorem. But we found the slope between the endpoints being 0, not because these numbers are 0, but because slope is 0 minus 2. These are the same, right? 0 minus 0 over 2 minus 0. So because we are trying to find the slope 0, we plug 0 into our f prime variable, solve for x, and we solve for x. This is cube root of 2, so no plus or minus, so just positive cube root of 2. Cube root of 2 is safely between 0 and 2, so at cube root of 2, this graph is going to experience a slope of 0. Okay, your homework, check your calendar. It's just going to be from the textbook pages, which you can find in your packet. There's no AP practice, so cross that off. No AP practice, just the homework problems. That's correct. Can I get you back? Yes.
Oh, I stuck it in one sheet, just like.